return, and that's our approximation to pi. So let's try it out. Let's say that the last term that we want is 1000 and we want to print the result. So I run it, and here it is. We get an approximation for pi. Now, in order to get the actual pi, or at least the pi to the precision that's used in Python, we can use math.pi. So you see here it's 3142559 and so on. The actual math.pi is 3.1415926 and so on. So you see, if the last term that we use is n equals 1000, then the first 3 digits of the correct pi and the approximation to pi are the same, but the 4th digit is different. So our task now for problem 3 is to actually figure out how many terms we need in order to, for example, have the approximation to pi, so this kind of thing, and the actual pi agree to the first 5 significant digits. So that would mean that we want that the approximation would start with 3.1415. So that would be agreement to 5 significant digits. So how to achieve that? So what we'll do is we'll first write a helper function, which would be agree to n sig figs. And what it would return is it would return true if x and y agree to the first n digits significant digits. Okay. So what are the arguments? So the arguments would be x and y would be floats. And we'll say between 1 and 10, y you'll see in a second, and n digits is going to be a positive integer. Okay, and the goal is, again, so let's say that x is this and y is this. So we want to return true for n digits equals 3 because the first 3 significant digits are the same, but we want to return false for 31425 for n equals to 4 because they're different, right? So this is 3142 and this is 3141. So how do we do that? Well, so the way to do it is to say, okay, the first trick is we'll see what happens if we multiply, for example, math.pi by 10 to the power of 3. What we get is this kind of thing. So what we get is 3141 point whatever. And then if we then convert it to an integer, what happens is you truncate the number, right? So you just get 3141. So the trick is we do this with math.pi with x, for example, and we do the same thing with y. So let's do this with Leibniz pi 1000, for example. And we compare those two. And if they're equal, well, that means that x and y, or math.pi and Leibniz pi 1000, agree to the first 4 significant digits. And if they're different, then they don't agree, right? So that's exactly what we'll do. We'll say if x times 10 to the power of, and we'll figure out the power of what in a second, convert it to an integer. If that's equal to this thing, so y, again converted to an integer, then they agree to n digit significant figures. So what should this be? So we said if we multiply by 10 to the power of 3, then what we get is we get the first 4 digits. Okay, we want to get the first n digits, so this should be 10 to the power of n digits minus 1. So for example, if we want 4, then we need to multiply by 10 to the power of 3. And this should be the same. So this should also be 10 to the power of n digits minus 1. Okay. So if they're equal, then what should we do? We should return true. If they're not equal, we should return false. So we can just say return this. So if those two terms are equal, then x and y agree to the first n digit significant digits. And if they're not equal, then it will return false. So let's take out this factor so that it looks nicer. So the factor is going to be 10 to the power of n digits minus 1. And this is going to be x times factor. And this is going to be y times factor. And we just return if those happen to be equal, then that means that they agree to n digits. And if those happen to be not equal, then the equality is false, and we'll return false because they don't agree. So let's try it. So I'll say agree to n sig fig, and I'll say, let's say 3, 1, 4, 5, 3, 1, 4, 6. Do they agree to 2 significant figures? Yes, they do. How about 3? Yes, they do, because they both start out with 3.14. How about 4? They don't. Okay? So that's our helper function. Now we are ready to write the actual function. So the question that we're asking is, what should this last n be in order for us to be able to say that the approximation and the actual pi agree to n significant digits? So what's the strategy here? Well, the strategy would be essentially have this loop, and then every time we add a new term to s, we'll check whether we're done, whether now we can say that our 4 times s actually agrees with math.pi to whatever number of significant digits. So let's do that. So this is a while loop, right? Why is it a while loop? Because we need to keep adding stuff to s up until the point that we have an agreement. So while we don't have an agreement between the approximation and the actual pi to n significant digits, we should keep adding those terms. Okay. So we start out with s equals 0 and with n equals 0. So if you add up 0 terms, then s is 0. And then we say, so while there is not an agreement between math.pi and 4 times s to n significant figures, so while there is not an agreement like that, we need to keep adding terms to s. How do we do that? Exactly in the way that we did before. And now, because it's a while loop rather than a for loop, we actually need to increment n manually by 1 every time. So, okay. So that's the loop. We check every time whether we've reached the agreement or not, and then we increment s by another term, and we increment n. Now, one small thing that we need to pay attention to is what exactly are we looking for here? So we need the number of terms required to obtain an approximation of pi. So it's the number of terms rather than the last n. So let's make sure that that's what we're actually computing. So if s equals 0 agrees with pi to n significant figures, then we're done already, right? And then we'll return n as we should. So that's good. So here we're saying we start out with n equals 0. We add 1 to n every time. So at this point, s is the sum of the first n terms. Because think about it this way, you add the first term with n equals 0, and then at the end of the loop, s is the sum of the first n terms. And now we check again. So the second time rather that we check, n equals 1, and we have one term that we've added to s. So that means that when we stop, we actually have what we want. We have the number of terms that were added to s. So n is the right thing to return. So, okay, let's try it out. So let's see how many we need in order to get agreement to, let's say, 3 significant figures. The answer is 119. How many do we need in order to get agreement to 4 significant figures? That's 1,688. Okay, so that's it.